one question I had, like Lollapalooza is still a thing, I guess.
As I was reading that,
Yeah,
I was like, is this going to
this is a
resonate?
dated reference. Yeah,
Yeah.
Yeah, it is a thing, and it is the most mainstream music festival that exists right now, as far as I know. So,
really.
Way to be mainstream, Brian.
Okay, because I mean it's definitely a very Gen X phenomenon, and but it's still, but it is it has continued, and because this was like a Jane's Addiction thing way back in the day, and then it was a festival that brought in a bunch of different kind of eclectic kinds of music. And then like the idea of like palooza as a suffix, I kind of went down that rabbit hole.
Dude, I was right there with you too, and I was like, is this maybe as durable as gate as a suffix? Maybe slightly less durable?
Ooh, we need a palooza gate, or is it gate palooza?
There we go.
Do we go?
Why not both? But very different things.
Very different things. Yeah. Would you rather go to? Would you? I think palooza gate. Which do you prefer, Palooza Gate or Gate Palooza? Gate Palooza sounds kind of like a multi-day festival
is
for
like
all the scandals.
oh yeah, I think it's like a scandal-ridden administration. It would be. This is just like Gate Palooza.
Isn't Gate Palooza like many different stages with different scandals on every stage? And like, oh man, go to the Pizzagate stage. They absolutely nuked it. That was just crazy over there. Exactly, crushing it over there. Yeah. So I think I would prefer to go, but then I kind of like clearly. Palooza Gate is obviously the scandal that brings down Lollapalooza. I assume, right? I think we agree on this.
Gotta be.
All right, right. And then the other, like, and I'm wondering if you went down this rabbit hole as well. The like validation versus verification. Did you know that I kind of like changed up on you as we were talking about this? It went from validation palooza to verification palooza.
And I didn't notice that.
And amazingly, this is something that people have got strong opinions about. I don't even know which is which. So anyway, here we are at Palooza Gate. So I went with verification Palooza. So now we've taken more detail than anyone wanted to know. I come up with our dumbass title. It's like, can't you jokers just like stick to Simpsons references and be done with it? So we've got Greg and Rain here, and we're talking about software verification, and because I think there's a lot that is here, and a lot that that different folks have done, certainly at Oxide, but we know well beyond Oxide as well. And I wonder if maybe we could start, Greg, with you, and because a couple of months ago you were demonstrating for the team how you used TLA Plus to actually do some model verification of some software that you were working on. And the thing that I loved about this is you got there from a concrete issue that you were working on. So do you want to describe a little bit about the issue and kind of where you got to and what model checking is and how it was valuable for you?
Yeah, sure. There's a whole lot to unpack there. I wish it was only a couple of months. Believe it or not, it was all the way back in January that we did the demo that you're thinking of, and it's just been trying to implement all of these things since then. But yeah, so I have been working for quite a while on various aspects of live migration of instances in our system. And last week's show, we talked about some of the, well, not we, I wasn't here, but y'all talked about some of the various aspects of what it takes to take a running virtual machine and move it from one virtual machine monitor to another, potentially on a different machine. So there's all the mechanical pieces of that, and I've worked on some of those, but lately I've been focused a lot on the orchestration process for this. So given that we want to move a running VM from one compute sled to another, how do we get our control plane to coordinate all of that and stand up the appropriate VMM processes and get everything to invoke the right things at the right times and monitor all the state and everything like that that needs to be monitored in order to get one of these things moved over. So the process for doing this is a pretty gets to be a pretty gnarly distributed systems problem in relatively short order. You've got two separate virtual machine monitors running around as part of your migration process. Those are both reporting status to two separate processes that we call the sled agents. These are the processes that run one per compute sled that coordinate all of the activities on the sled. Those are reporting status back up to the Nexus, which is a separate application that is doing all of the main control plane business logic, and that has that hosts all of the external Oxide API endpoints that you go and invoke. So you got all of these different things talking to each other. The Nexus is off talking to a database that it to which it reads, to which it writes and reads, and from which it reads the state of individual instances, so that it can coordinate various things that are happening and respond to API requests correctly. So you got all these different actors running around. They can crash at various times. They can go away at various times. Their responses to each other could be delayed by arbitrary amounts of time. Just standard, concurrent, all kinds of interesting concurrency in there. So when I started designing the live migration procedure that the control plane runs, I did one draft, and it was a pretty shallow draft. Just here's generally what the steps look like. Okay, that looks pretty good. So then I did a
And is this
second
draft like
and,
in your
yeah, go ahead.
notebook, Greg?
Yeah, this is in my
there
notes.
something you're-
Yeah.
Oh, right,
So,
okay,
so
yeah.
this was
No, but
this was the draft of the design document that turned into
Right, okay.
one of our requests for discussion. So that for the
So
for
you're
the
not
Oxide
yet writing
plane
code.
on
You're
the
just kind
phone.
of writing down. Okay,
Yep.
got it. Yep.
Yep, that's right. Yeah, so just trying to get all of this design on paper so that I could put this into a request for discussion and have folks at Oxide review it, so that, because it's a lot cheaper, of course, to deal with design issues much earlier in the design process than, hey, look, I implemented this thing and it's 5,000 lines of codes and none of it's right, and
Well, so
the algorithm's
actually,
fundamentally broken and that sort of thing. Go ahead, Brian.
so this is kind of an interesting, because I think that there are some things that you really need to just like get in and prototype to really iterate on.
Mhm.
And then there are other things where you're just like, actually, you're just going to get into trouble by, and when you get this a distributed system and you got a lot of pieces moving and a lot of possible failure modes, getting in there and quote, just getting something working sometimes sends you off in the wrong direction, because if you really do need to, I think, sit down in your notebook and be like, what actually are the steps that needs to happen? What can go wrong in each of these steps? And you are almost disserved by a prototype sometimes.
Yeah, I think that can be true in some cases, and I think that for the sort of system that we're talking about here too, there's also just a lot of things that we knew up front from other operations that we had
Hmm.
written and other code that we'd done, where we knew that there were certain requirements that we were going to have to meet. So this gets into things like we use a scheme called distributed sagas to do certain long-running operations in the control plane. And the idea is that you take a complex task and you break it into individual units that can be done idempotently and that can be undone. And that allows you to set things up in such a way that you can guarantee that your entire task either completes or gets undone and the prior state gets restored. Even in the face of your executor crashing in the middle of what it is that you're trying to do. So we have a bunch of requirements around that we knew we were going to have to uphold, and I wanted to be able to go through and say, yeah, every step of this migration procedure is going to uphold all of these properties that I know we're going to have to uphold, because we just talked about this when I was writing this a few weeks ago. There had been a control plane meeting where we'd sat down and gone, yeah, we really got to be careful about this and make sure that this stuff's getting verified correctly for all of the things that we're writing. So yeah, there was this definitely had a lot of design upfront aspects to it, because I knew that there were a lot of things we had to get right, and I definitely wanted to try to make sure that I was thinking them through correctly before trying to get into having too much fun in the code itself.
Yeah,
So
totally.
yeah,
Sometimes you got to know in
knowing.
the prototype and know in the waterfall, and this is an
Mhm.
example of when you really want a waterfall.
Yeah, so when I started doing the design document for this, and just making sure that I had what I thought was a reasonable thing in my head, like I said, I did a first draft of this, and it was pretty straightforward, and it looked okay. So then I did a second draft where I started fleshing it out, and then I wanted to do the thing that I was actually going to put up for peer review, and the third draft started out okay. But about halfway through, I pulled it up to look at it again. I still have this around. About halfway through, it starts to devolve into this long list of to do XXX. There is no way this design could possibly work. Here is an 11-step race condition involving 3 different sleds that causes us to leak the fact that we're migrating this instance and we never think it's running again. And here's a different 11-step race condition that makes it so that the instance is running in 2 places at once. And eventually, as I was looking at these, I realized, hey, wait a second. Like, a variant of one of these races is actually a problem that we have today. We have a bug where, due to the actions of the I mentioned the distributed sagas earlier, the saga that's responsible for creating and starting a new instance, it's possible to have a sequence where we invoke one of these and it starts your VM, and then the control plane process that's doing this immediately crashes before it records that the VM was successfully started. But your VM is started, so then the guest software running in there shuts the VM down. Now it's supposed to be stopped. And we go back and replay the step that starts it because we didn't get to the end of that step yet. And now you have a VM that's running even though the last expressed user intent was that you were was to stop the virtual machine. So I remember, like, I came up with this on a Friday and came back on Monday and kind of started nagging some people about, hey, is this a real thing? Have I identified a real issue? But that was about the point where I decided, all right, you know what? Thinking about it really hard is not going to be sufficient here. Like, this system is too complex. There's too many ways to interleave all of these concurrent operations. It's time to break out the big guns. It's time for formal methods, and that's
It's formal time.
and that's what led me to get out all the TLA plus material again, and what led to the demo you were talking about at the beginning.
So could you speak to your own origins with respect to TLA plus? Because I think you got exposed to this at Microsoft. Is that right?
Yeah. So just as background, the whole discipline I'm gonna be talking about here, is this discipline of formal methods, which are the practice of describing systems in a very mathematically rigorous way, so that we can design them and specify them and hopefully verify them. Not that I'm going to go all in on verify here. I'll probably slip up and say validate like a third of the time, but we'll go with verify. Using the tools of mathematics and formal logic that are available to us to reason, very very formally and powerfully about these systems. Yeah, I mean, in terms of my own history with it, I think I first came across TLA plus specifically back in like 2010. 2011, something around there. I was working in the Windows kernel team at the time, and was working on synchronization objects up in user mode, and had a colleague who worked on some of the kernel mode counterparts to these, some of the kernel mode synchronization objects. And I was building something new and having a lot of trouble, like getting everything to work right and getting it not to just crash at various points. And my colleague was like, hey, here's this thing for formally, specifying the different steps that these algorithms can take, and like trying to come up with stronger inferences about them. I can't remember if he mentioned that it had a model checker at the time or not. But I was a couple years into my career, and I was basically like, yeah, I'm really stressed out about getting this thing delivered. So nope, I don't know what I am. I'm gonna forget about that for now. Like, I'm way too busy to deal with this. Some years later, I forget how I did this, but I first came across Hillel Wayne's writing, and Hillel is a consultant and writer who specializes in formal methods and in TLA plus specifically, and wrote the TLA tutorial at learntla.com. And there's, in addition to all of his writing about formal methods, there's a lot of interesting stuff that he's written about software verification more generally, and about engineering practice and engineering as a profession. That's just like bread and butter stuff for me that I find really interesting. So that was kind of a nice return to it a little bit. And then it was a reminder that this stuff existed. Then the first time I think I actually used TLA for anything reasonably practical was in 2019. I was on leave and had a little bit of downtime, and used it to reproduce a bug that I had once written into the Win32 critical section that could cause a crit sec to be not held but have a waiter who was blocked on it. And it turned out to be so so the issue was this complicated ABA problem in the state of the lock, where like you'd get somebody who acquired the lock and then dropped it, and they thought that like the lock state hadn't changed and it was somebody else's job to wake waiters, but in fact the somebody else had left the lock long ago. And what I remember about this bug was that I had written it, and then it had gone through like the first step in the Windows engineering and integration process to get to a slightly broader internal audience. And then we started getting like these occasional reports of like, hey, in stress testing, this thing is failing. We're seeing these locks get abandoned. So back the thing out. And it took myself and two colleagues on that team a few days really to figure out what was going on. Like one of my teammates came in a few days later and said, okay, I was thinking about this last night. I think I finally got it. What if like this and this and this and this? And we looked at the code and we realized, hey, that's exactly right. Like that's what's going on here. And we fixed the bug. So that was a couple years prior, but in 19, I decided, okay, like as an exercise, I'm gonna try to reproduce this and see like what we would have gotten out of a TLA plus model for it. And I was very impressed upon by the fact that the model checker took the bug that took probably 50 engineer hours to find and pinpointed it in about 25 minutes, and then verified the solution to it in another 25 or 30 minutes. That made a big impression. I was very impressed upon by what a powerful tool this was for reasoning about all of these different ways that we could get these different interleavings of different threads working on this lock, and that we could make sure that there wasn't any deadlock and all of our appropriate invariants were upheld at each and every step.
Greg, I
Yeah,
love
that is
that in
awesome.
particular because you started from, I don't have time to learn this thing, to holy crap, if I had learned this thing, it would have saved me so much time.
Oh man, yeah, I definitely kicked myself a few times after realizing, boy, this would have saved me a whole lot, like back when we ran into this. But youth for one thing, I was pretty early in career when that happened, so I will give myself a little forgiveness there, and better late than never. It's nice to be able to use all of these tools now.
Well, after the ignorance of youth comes the hubris of experience. So some of us transition just, from one to the next.
Well, so I mean, a lot of my philosophy with these tools too is that I want to use these because I know I'm going to make mistakes, and I know that there is no way I'm going to be able to think hard enough about any of these problems to be able to actually like suss any of this stuff out to begin with, and so it's for me. I really like having the extra assurance that comes from having the computer do the really hard work of thinking about all of the different ways that things can be interleaved and can interact with one another, and having it hold up the various problems that we can get into in designing systems like this. So it is if nothing else, experience has taught me that yep, I write a lot of bugs, and it is nice to be able to head as many of those off at the pass as I can manage, and these are nice tools for doing some of that.
Okay, so with that, I mean, do you want to explain a little bit what TLA Plus is and what is a model? How do you generate it? What are we doing when we're actually checking the model?
Sure. Yeah, so TLA is the temporal logic of actions. The plus is for some set theory stuff that I candidly did not take enough discrete math in undergrad
Also,
to understand.
is the plus
So,
in
yeah.
superscript? It looks like the plus is in superscript, which is like up there with Unix being in small caps as a way of just angering people from a typesetting perspective. But
I am. I mean, the way I have not, it might be typeset in superscript in some places, but no one that I have seen is going to get particularly antsy about just having it in regular script.
I'm sure there's someone who only uses in superscript, being like, I told you these people are slobs. These people who don't put it in superscript, they're slobs. Anyway, sorry, pretty continue.
No, that's fine. So the idea is that we take a combination of set theory and formal logic and propositional logic and add some notational affordances to be able to talk about how a system evolves over time. And in doing that, we were able to generate the way that I think of it is like big graphs, big execution traces of the way that a system is allowed to proceed through a set of executions. So the idea is that like a model, what a model really kind of boils down to is it's a big old logical predicate. It's the disjunction of a whole bunch of different individual predicates that specify, I have the universe, and I have some set of variables in the universe that I care about. And the variables can in theory take any arbitrary value. I can have some variable that is 3, or it's some string, or it's some, unique model value that, is not equal to anything except itself, or it's a set, or something along those lines. There's a few different, individual quote unquote types of things that we can have in the system. And what our model is a specification of values that it is a set of predicates that tell us what values belong to like our and I'm really kind of struggling for the words here, but what values fit into our model, like which ones are part of the set of states that can be reached by the system that we have specified. So usually the way that you would write that is you would say, in the initial state, my variables can have any of the following values. And that could be like, this is guaranteed to be null, or it always starts out as 0, or it's like anything from 1 to 10 or something along those lines. And then you take the disjunction of that with a special predicate that says something of the form of, if the variables have the following values or meet the following conditions in some prior state, then they take on the following values in the next state, and that next state becomes part of the universe of part of the selection of states that are allowed by the system that you have specified. So you are writing a set of rules essentially for how you can proceed from one set of variable values to another at each individual step. And then you can so that's your specification of your system. Beyond that, what you can do is you can express sets of predicates over those variables that are supposed to be invariant over the variables. So you can say things like, this thing should always be an integer of some kind, and if it's not, then I have screwed something up in the model. You can get into things like, so for the example I gave earlier, we can have a rule that says, if the instance is currently running, like if the variable that I have in my model that says what the state of the instance is set to running, then the user intent, the last thing I heard from the user, had better not be that it is stopped. Like that is, if I see that, then that's a problem. And then there is software that takes this thing and enumerates all of the different possible states and executions and interleavings thereof, and will check for you to see if your invariants are invalidated at any particular point. And if they are, then it will scream. And it will scream in an especially useful way where it will show you the TLA model checker, TLC, will show you the set of steps that it took to reach the broken invariant. So you can look through there and see like this whole like, oh, this and then this and then this and then this and then this, and these like 15 steps together led to this particular invariant being violated, and this is the thing that I have to go figure out how to fix.
And how often is it a bug in the model? Because as you're developing the model, presumably you also have things where it's like identifying one of these interleavings. Like, oh, actually, I realize that the model does not represent the system accurately in this regard.
Yeah, I mean, sorry, go ahead and finish, please.
No. Yeah, go ahead. So they just like how often is it a bug in the model versus the model is correctly representing the program, and therefore it's a bug in the program rather than their thinking?
I mean, so if you're doing a translation, it's at least like sometimes that this happens. I have not like translated a whole heck of a lot of code, at least as I have been doing these. It's mostly been sort of new design. So I tend to think of bug in the model as something more along the lines of like, whoops, I referred to the wrong.
Yeah,
I referred to the wrong variable there, and so now I have an invariant that's being violated, but it's because I screwed up, right? Like this wasn't what I meant to express. I think that a common thing that can happen is that you like the common failure mode for me has been like oversight of one kind or another. Like there's this particular case, and I just like didn't think of that, and so I specified this behavior that I thought was going to work, but is missing like some particular condition that needs to be checked in order for everything to hold up correctly. So like I was working on one of these today. I'm going to try to find the example that I had in here. Yeah, something along the lines of, we have to oh yeah, it turns out that we have to check to make sure that the thing that is currently in the table is the one that we're trying to remove from the table, because like just doing this, rote replacement is not semantically correct for the particular thing that I am modeling. My experience is that like this sort of mistake, I wouldn't even call it a model in the bug, or excuse me, a bug in the model necessarily. I tend to think of it more as just, yeah, like you didn't think of that quite right. You kind of left it underspecified, or here's a thing that you didn't picture just yet. One thing that is fun about this is getting into dialogue with the model checker almost, where you come up with something and you have your set of invariants, and all right, here's my proposal for how we're going to uphold these, and checker says no, and the checker says, oh yeah, you messed this up in this particular way. Okay, well, I'll add this and add this check here and this step here and deal with that. And you send it back to the checker, and the checker says, yeah, no, but what about this other thing? And for a while I was doing all the design work for migration orchestration, I was just sitting here like having a back and forth with the model checker about like, okay, what about this design? What about this design? What about this design? And if it's actually like even in the commit history, like for the models in our internal docs, where it's like, okay, this is still failing because of this thing. All right, we fixed that, but now it's failing because of this thing. And it's honestly like kind of fun to have the automated conscience sitting there telling you what is wrong with all of the stuff that you've done so far.
When you're able to do very rapid iteration, but it's a rapid iteration at the kind of the highest level of the system, of where you're actually thinking about the system in its most abstract, before you can make much more costly mistakes by actually building it the wrong way.
Oh yeah, absolutely. I mean, one of the things that is really valuable about this, like one question that I think, Brian, that I think you asked when I first showed some of this stuff was what the procedures are for translating one of these things into actual code, and it depends like kind of on what system you're working in, but generally automation of turning a formal specification into a piece of executable code is a very, very difficult problem. It would have been especially difficult in a case like this. Like the prototyping that we'd be talking about here would be, in order to ultimately implement the design that I settled on, had to go change there were a bunch of changes to our internal database schema, and I had to update all of the code that was like dealing with all of the types that were dealing with the schema, and I had to add all the APIs that dealt with all of these internal interactions between these various things, and like thousands of lines of Rust ultimately to implement all of this stuff, and a lot of time spent on it. And yeah, like trying to do all of that just to get to a point where we could find out that here is like this subtle, this particularly subtle issue that we may not even have found any of the subtle issues.
Totally. Yeah.
And I think too, like that's a point too that I think is worth emphasizing. With the original bug that led to this whole affair, in order to hit it, you would have needed a very precise set of racing steps to happen, where a Nexus process crashes at exactly the right time, and while it is coming back up, your customer stops a VM, and the VM stop gets recorded, like just recorded enough, but not quite enough, in order for this whole thing to get replayed and deal with the and create the condition that we were trying to avoid. Can you imagine writing the integration test for that? Like the set of controls that you would need in order to be able to get like this specific sequence of crashes and everything to happen. And that's if like that this bug is in here in the first place. So
yeah, I was gonna say that's assuming you can debug it. I mean, this is the kind of bug you're going to see exactly once, and you've got to hope that you've got enough information that's been left post-mortem for you to be able to figure out what actually happened here, and then rely on kind of the putting it all together in terms of what has happened, and then the ability to reproduce it. So it's much easier to think about it in terms of the model.
And with the rare ones too, as I'm sure we all kind of appreciate, when you write your fix and you go to test it and the bug doesn't happen, and is that just because you took it and now it's even more rare than it was to start with, or is it really
Totally.
gone and your fix is really working? And yeah, being able to just iterate over all of this stuff exhaustively is a very, very powerful set of techniques for dealing with these things.
When it's also, especially if you've got a fix. I mean, having just had this recently to myself, where I had a fix that was almost complete, but not complete, and not actually complete. But it made the bug so much less likely to hit that I deluded myself into thinking that I'd actually completely resolved the issue. And it's very when you don't have that higher level of abstraction to be able to reason about. It's easy to do that. It's easy to think that you fixed it because the bug used to be here and now it's gone away. It's like, well, actually, now you've made it much less likely. Congratulations, but you actually haven't completely fixed it, and there's still a window, and that's where your model checking can really come to the rescue. So can you just talk about the mechanics of this a little bit? Because you were using, I think, you were using PlusCal, right? Am I remembering that correctly?
Yeah, for the model I demoed, yes. So pure TLA plus is what I described earlier, which is you go and you write all of the predicates by hand. There is a domain specific language called PlusCal that is more procedurally oriented in the sense that it looks a lot more like there's a Pascal-ish dialect and a C-ish dialect, and it looks a lot more like a straight line set of procedures and functions that you have written, and I think can be a little bit more familiar. Certainly it was for me getting into modeling for the first time. So you write one of these things in this more procedural style according to the rules of the DSL, and then there's a translator that turns that into actual TLA plus for you by taking your it does the insertion of all of the, like, I have this procedure and it's at this particular point in the procedure. It does all of the program counter stuff and generates that for you so that you don't have to think about it as much. The Learn TLA resource I talked about earlier is PlusCal oriented. I think for the first, probably I'd say 80% of it or so. It's a good way to get started and with more familiar concepts if you were brand new to this sort of thing. And it is also I think especially good for taking existing code and trying to translate it into something that can be model checked, or taking an existing procedure and turning it into something that can be model checked. I have done a little bit since then of just doing things in pure TLA plus. There is a set of examples. The collection is called Pragmatic Formal Modeling, and I've got links to all this stuff that I'll kick over and we'll make sure we get in the show notes. But there's some examples of things that you can do to model systems and these examples are written like just in pure TLA, no PlusCal in sight. And that kind of put me on to some of the power that you get out of expressing things in just like in this pure form. I think if you were asking me like to pick one, if I were doing something that was very clearly like procedurally oriented and or that has like a lot of, I find it easier to reason about like locks and waiting for conditions and translating code that looks like that in PlusCal for things that are sort of interacting state machines where you have a bunch of like, if the widget is in this particular condition, then it can go into this state or that state or the other state. That can actually be really, I've found that can be really natural to just write in TLA. And it turns out actually that the migration design specifications that I mentioned, I ended up just doing those that way because it turned out to be the easiest to reason about, like, oh yeah, this is how all of these individual pieces of state are allowed to change given the different things that are going on.
Oh, interesting.
At some particular point. So, yeah, I mean, it took reading some additional examples to really get a sense for like, oh yeah, here's how I would express all of this stuff, and here's what idiom kind of looks like, and that was really helpful in figuring out how to actually put those things together.
And so were you able to reproduce the bug that you thought you had found as you're beginning this design? You're like, I think I've got this bug in the extant system. Were you able to reproduce that bug using your model?
Yeah, so the first and it feels a little bit like, so I was able to do that. It feels a little bit like cheating because like we had already looked at it and it's like, yeah, this is kind of already there. So am I writing this model in a way that is going to get the model checker to show me
Right.
the bug that I know that I already think is there, or am I doing this right? Like, am I being fair about all this? But I think we decided it was the latter. And the nice
But
thing about it was that it was, oh yeah, sorry, go ahead.
you use this pattern twice, right? I think it was kind of interesting that you used this when you were first kind of experimenting with this in 2019, and maybe that's just a good way for as you're kind of getting your feet wet with these things, like actually going and reproducing something that you're already aware of, and
Oh
let
yeah.
this thing find it is actually a pretty good way to understand the tool chain, I imagine.
Yeah, I think that's true, and certainly like there is, when you're learning to do something like this, there's no substitute for practice, and you can do all the reading you want, but eventually you kind of gotta, I think anyway, you kind of gotta just do some of them to really get a sense for how everything works and what works well and what makes things fit together nicely, and certainly doing that with an existing system that you already understand well is easier than is easier than trying for a first go round than doing something out of whole cloth. So yeah, I wouldn't necessarily say that the parts of our control plane that I was working in were things that I knew very well at the time that I was doing this. So I wouldn't. I was a little worried that I was misrepresenting something. But to your point, yeah, I mean the model checker was pretty quick to throw up the bug that we thought we had, and was pretty quick to verify a solution too. Like we go and there was a solution that we'd suggested that was essentially, yeah, what if we break this into two phases, and we have one step that says, hey, I'm gonna start an instance here, and then another step that actually starts the instance, so that if the second one like gets replayed, then it doesn't get started again because it already started once and then got stopped. And in principle, yeah, the checker's happy, and we went off and implemented that, and have generally been pleased with it since. I mean, to be fair, I don't know that we had ever actually seen this issue in practice, but it was certainly something that appeared to be there on inspection, and hopefully it will not crop back up as we continue doing more empirical testing and stress testing of the system and things of that
Well,
nature.
and I feel that that's also super satisfying and it's a good omen as a software engineer when you are discovering pre-existing bugs as part of your work. You're like, okay, this is like, I'm beginning to test this thoroughly enough or think about this rigorously enough that I'm discovering pre-existing things that were already here. I just feel, again, I feel it's a good omen. It's not necessarily a certainty, but it's you're going in the right direction, and you're thinking about the system in the right ways, or you're thinking about it in a way that hasn't been thought of previously. So did you end up? Did the models end up? Did you end up effectively checking that in side by side with the software, or what happens to the artifact that is the model?
So they're not in with the software, although they probably should be. I will have to get over my embarrassment at my probably unidiomatic and generally noobish TLA plus modeling, but they are at least checked into our internal request for discussion repo. So for the Oxide folks at least playing at home, they're present alongside RFD361. For the migration one, I would like to get it transferred over into the Omicron repository, into the control plane repo, so that it will just like be there as part of the repo docs. I also am looking to do that. There's an issue I've been working on today, actually, where doing some of the same modeling tasks to try to verify that, like, oh yeah, this proposed fix for this particular problem that I've seen is probably going to work out all right, and I would like to get that spruced up and put in at least into the issue comments, if not just checked into the repo as well. But yeah, I think it can be really helpful to have that stuff alongside. These things function in part as documentation of the way that the system is actually supposed to behave at a high level, and what was just let me see if I can dig up one of these things. Which one is this? So this is the is the configuration file. I want to get a sense of like how long one of these things is. So this is
I think it'd
like
be
load
really
of
helpful to
comments.
see one of the totally.
Yeah, so I mean this TLA model. So this one here, I'm looking at one of the ones that I did for the migration orchestration. The entire model file, including just like lots and lots and lots of block comments just to try to explain what's going on, is about 700 lines. And I remember like when the actual code was originally done, it was about 10 times that in total in the Delta. So, and spread across just many, many, many files and many components. And like I mentioned earlier, buried in the weeds of all of this stuff around how exactly do we write all the ORM code to go manipulate the database in the right way? And what do all of these individual like API endpoints look like? It's not boilerplate, like it's important stuff that we have to do in order to have a shippable artifact. Like no one's going to run the model, run the VMs on the model. But I think it is a much more concise way of expressing the intent of the system here.
And maybe that's a good segue too to Rain, to you, because when you begin to go from like, okay, so you've been using the model to kind of envision the system from whole cloth, and now we actually have a system, and now we need to actually verify the kind of the extant system, and then we need to be able to improve it, and we need to be able to fix a bug in it, and be able to know that we haven't kind of violated its invariance for the actual implementation as opposed to the model. And Rain, and testing is something that is very near and dear to your heart, and you've been working on things to use property-based testing, which is something that I have not used. So maybe you could. This is maybe a good segue to some of the work that you've done in that regard.
Yeah. So it's funny because the first time I was introduced to property-based testing was in the context of a model being defined, and then we needed to test that the implementation actually worked. So, so I used to work at Facebook, and I was on the source control team at Facebook, building the next generation source control server called Mononoke. And as you might have heard of, Facebook stores all of its code in a single giant repository with hundreds of millions of lines of code, last I knew. And
I mean, there's the mega monorepo. There's going to be a
Yes.
different term. This is like, monorepo, but like much larger. This is, it's amazing the scale.
It's pretty incredible. It leads to certain interesting trade-offs. So one of those trade-offs is that we had to build new source control data structures to support this, because the existing Git-like data structures didn't meet some performance characteristics that we needed them to meet. So my coworker, Jeremy Fitzharding, actually built out. So we did some design by hand, and my coworker built out the specification for the structure in Alloy, which is a cousin of TLA Plus, I believe, Greg. And actually, Hillel, I think, has some good writing on Alloy as well.
Yeah, there's Alloy is definitely in the same family. And Hillel does have some extra writing about it. I haven't played around with it a whole heck of a lot, except like a little bit last week, just to sort of see what it was like before sitting down here. So the thing about Alloy, I think, is that it has historically not been as strong at modeling concurrency. Like it's always been kind of a bag on the side until its most recent release, and it's gained some different powers for reasoning about concurrent systems and the flow of time and that kind of thing. So it is something that I'd like to revisit at some point. But yeah, Alloy seems cool in that it seems like it has a much stronger object model, shall we say, than TLA does. And I imagine that for the kind of I bet you that for the kind of system you're talking about here, Rain, that kind of the sorts of powers that it has in that respect were probably particularly useful.
Yeah, that sounds right. Yeah, that's my understanding too, that Alloy is good for modeling data at rest, I think is the way my coworker described it. But anyway, so we'd written out this model, and it seemed to check out, and we ironed out all the issues with it. But then when we actually went to write the code, we realized that the model was fiendishly complicated, and I think the code to translate back and forth between Mercurial, which is what we were using, and this model was like several, I want to say at least 1,500, probably 2,000 lines of code. So we needed a way to actually make sure that things like you needed to be able to do a round trip, and you needed to be able to exercise all sorts of edge cases. And so that's where I started looking into property-based testing, and we used property-based testing in a couple of ways. One of them was we took out random subsets of our gigantic monorepos and we replayed them, and we made sure that like all the invariants were upheld. We also synthesized random repositories to make sure that in all these sorts of edge cases, all the invariants that we wanted to uphold actually worked. So I think overall that was my first experience with property-based testing.
And Ray,
I think-
maybe
yeah.
do you want to just explain what property-based testing is, kind of the approach that, because it's and kind of its origins?
Yeah, so property-based testing originally, my understanding is that the first versions of it were written in Haskell. I think this comes from the 1990s, I want to say. And the idea behind property-based testing is that most of the tests we write, like in our normal use, are like, like you have a list that's like 1, 4, 2, 3, 5, you sort it, and the output you get is 1, 2, 3, 4, 5, right? And the idea behind property-based testing is that rather than testing for specific examples, you generate a bunch of random test cases that you hope will exercise all of those, all the different code paths you care about, and then you run them through your code under test, and you make sure that the answers there are correct. Now, there's a huge asterisk next to the how do you make sure that the answers are correct, but that's the overall view of property-based testing. I think there's kind of two different generations of property-based testing libraries. One of them is one that I'm sure a lot of folks have heard of. It's called QuickCheck. QuickCheck is kind of the original property-based testing library. It has been in use since the 90s, and I know that it's in use for things like automotive design, where you want to make sure that your car's software behaves the right way under edge cases and so on. The next generation of property-based test systems was originally actually in Python. It is called Hypothesis, and in Rust, the port of Hypothesis to Rust is called Proptest. I'm going to offend some people by saying this, but I think that nobody should use QuickCheck at this point. Like QuickCheck, and I'm going to go into why. But Proptest is like if there's one takeaway that you have from this, it is that if you're using Rust, you use Proptest. Haskell has Hedgehog for the same thing, and in Python, of course, there's Hypothesis. And all of them have a design that is better. And I'm going to talk about how it's better. So with property-based testing, I mentioned earlier that property-based testing is all about generating random values. Now, those random values tend to be pretty big. And so often, like, you will generate a value that's, for example, if you're starting a list, you might generate a value that has like 500 elements or something like that. Now, when you're actually like trying to debug test failures, if you're just suddenly presented with here's 500 elements and you need to go, figure out what's going on here, then that can be really hard. So the other bit that property-based test frameworks provide is called shrinking. And the idea behind shrinking is that after the test framework finds a failing case, it tries to reduce the size of the input in a way that it ultimately finds the smallest input. And the algorithm for that is pretty straightforward. You just kind of keep throwing smaller and smaller inputs at it and until you find the smallest input that fails. The modern property-based testing libraries like Proptest are a lot better at shrinking than the previous generation. And so they require a bit more effort to use, but I think you get so much more out of them with shrinking that it ends up being a pretty clear win.
And so then how do you use them? And how do you, if I want to use,
Yeah.
I've got a Rust crate, I want to use Proptest, like how do I get started?
Yeah, so with Proptest, you can. So there's a library. It's called Proptest. You import the library, and I'm gonna just paste a code sample here. And so let me see. Wow. Okay. So it ate up all the indentation,
Discord.
sadly. So here we have a couple of different examples of property-based tests for a for a sort function. So in this case, we are testing a function called mySort, and we have two property-based tests here. One of them is that once you've sorted the input, for every pair that's in window and output.windows2, we make sure that the previous element is less than or equal to the next element. So that's a pretty straightforward invariant that you want a sort function to uphold. I think that this sort of invariant, if you spot it, it's great, but often it ends up being pretty rare in my experience. So for a sort function, I think it's pretty clear, but I've found a lot of other real world use cases where it's very hard to find these sorts of invariants. I think the more interesting kind of invariant, and the one that I think really exposes how powerful property-based testing is the second kind of example, which is where we test our sort against, in this case, a bubble sort. Over here, what we do is we have our system under test, which is mySort, and we also have some sort of simplified model of how the code should work. In this case, it is a bubble sort. It could also be, for example, the sort in the standard library, which is probably correct. And so we run our input through our function, and we run it through the function that forms our model, and we compare that our output is the same as the bubble output. And this sort of, I think that this general pattern of testing is much more common than most people think. And I, as someone who's used property-based testing for a long time, I'm always on the lookout for okay, what other pre-existing work of art can we compare this to in order to make sure that our system behaves in a certain way?
Yeah, that's really interesting. So when you say you're on the lookout, what things are you looking for? Because clearly, if I were taking one system and replacing it with another, or another implementation, for example, very useful because I've got my Oracle is the extant implementation.
Yeah, exactly.
But it gets rockier when we're kind of doing new stuff. But so when you're on the lookout, what are you looking for? Are you looking for kind of subsystems that we have analogs for elsewhere, or what are you looking for exactly?
Yeah, usually there's subsystems that there's smaller components that might have pre-existing solutions. Often what I found is that there is some other way to express a particular algorithm or data structure that has a worse time complexity. So is less efficient in some way. So I will put in the effort to actually write a second implementation that is facially correct and has, even if it has a worse time complexity or space complexity or whatever, and then run tests through both of those to make sure that they're the same. So often, you do have to put in a lot of extra work, but in my experience, it's work that has paid off over and over again. I found probably over 100 bugs via property-based testing at this point over my career.
Wow. That is really as you're saying that, one thing that I'm thinking about is we write a lot of no standard code, and you're operating under certain constraints under no standard. You actually are trying to implement things that actually are available in the standard library, and that would be an example where it's very easy. Your Oracle is the thing that actually has that uses the standard library, and you can compare that very directly and know that your no standard implementation is correct before you actually have to debug it in an embedded environment.
Yeah, that's sort of more constrained implementation is a pretty common approach.
Yeah, that's really interesting. So, and maybe worth describing the kind of concrete example that you were showing us in terms of prop testing and where this came up and kind of the software that you were writing, and how you found something that could act as that kind of oracle.
Yeah, this is actually a really cool example because I thought that this is just a really fun and interesting use of property-based testing. So I wrote this crate called Bufflist, which I just posted a link to. So this represents a segmented list of bytes chunks. So the context here is that usually when you're working with byte buffers in Rust, you have something like a vec-u8 or a bytes if you're fancy. You can use the bytes crate. All of them are contiguous chunks of bytes arrays. So if for example, if you're storing like 20 gigs of memory or 20 gigs of data, like say a disk image, you would need to do a contiguous 20 gig allocation. That can be pretty inefficient. So a different way to store bytes data is as a list of bytes chunks, or in particular, a queue of bytes chunks. And the idea is that you can read data off of the beginning of the thing and go on until the end, and the data structure internally keeps track of making sure that you're reading the right bytes and you're not skipping over bytes and so on. So for this data structure, I needed a cursor type. So for those who are unfamiliar, in Rust, there's this wonderful notion of cursor types. So if you look at standard IO cursor, then that is a type that wraps any sort of contiguous byte array, and it provides a read implementation on top of it and a seek implementation on top of it. It logically represents some sort of pointer into this data. And so the cursor type it's actually, like, if you look at the implementation, it's pretty straightforward. It's a really useful type that works across any sort of contiguous byte buffer. However, what we have here is a discontiguous byte buffer, so cursor doesn't work for that. So I needed to write my own cursor, and the cursor for discontiguous byte buffers is actually significantly harder to write than the standard IO cursor.
Yeah, totally.
Because you have to keep track of all sorts of fiddly indexes. You have to make sure that you're reading past. You aren't reading past the end of something. You need to keep track of all of those things. So I needed a principled way to make sure that my cursor was correct. And the thought that came to my mind is that why don't I compare my cursor against the standard IO cursor? So what I did to address that is I wrote a test which generates a random discontiguous buffer, like a Bufflist. It combines that into a single bigger list. And that's something that is very inefficient, but it is okay to do in a test, right? So that's kind of where you start seeing the power of Proptest. After that,
and this is a very concrete example we were talking about, where you've got different constraints, where the reason Bufflist exists is because it's going to be processing these galactic amounts of data. But you actually don't need the galactic amounts of data to be able to test all of these various edge conditions.
Exactly, and so that's where you can like for smaller inputs, you can be sure that Bufflist works properly. And so I just pasted a link to the test. And the thing this does is it generates this Bufflist, it combines this into a single thing, and then it also generates a set of operations on cursors. So the set of operations are set position, start, seek end, current, read, and so on. So you have all of these different examples of operations you can generate. And then what it does is it applies these operations to the system under test, which is our cursor. It applies them to the oracle, which is the standard IO cursor, and it makes sure that it all checks out and all returns the same answers. And this ended up finding 6 separate bugs. I remember fixing one bug, and it's like, oh wow. So this ended up finding 6 separate bugs, and then after the 6th bug, it was like, pass, and then I was like, yeah, and at that point it was like pretty
Were you?
clearly correct.
I mean, that's a boy. That is a lot. At some point, and I know I've sort of had this where you're just like, okay, did I do anything right in this code? Like, how many bugs are there here? It's like, all right, this is exactly the kind of code that is so hard to get right in terms of where you've got, as you say, it's all these fiddly little edge conditions where it's easy to envision how you could have. Yeah, that is really powerful. Can I ask you, what do these strategy decorators denote?
Yeah, so this is getting into a little bit of the weeds, but so the way Proptest works is that the way you generate random values is by creating strategies of that type, and a strategy is simply a way to generate random values, but it also carries information on how you can shrink values into smaller ones, and it integrates both of those things together. And so strategy is a combination of those two things. So in this case, if you look at line 19, there is a Bufflist strategy. A Bufflist strategy is a strategy that generates a random buff list. And the function's right below there. And the way it does it is it generates a vector of 1 to 128 bytes. And then it combines. It generates 0 to 32 vector of them, 0 to 32 vectors, and then it combines them all into a single buff list. So that's what that is. Now, the fancy thing about Proptest is that this is actually more clever than it looks, because the prop collection vec function that is called here is also carries information on how you can reduce the size of the vector and reduce the size of the elements inside it. So all of that information is carried along with the constructor, and this is the thing that distinguishes Proptest and Hypothesis and the other new generation property-based testing libraries from QuickCheck, because in QuickCheck you don't carry that information along with it, and so it becomes much harder to do shrinking.
Wayne, how would you contrast this with fuzzing? Because it seems like there's some kind of similar properties here.
Yeah, so property-based testing and fuzzing are actually very closely related in many ways. So usually when people refer to fuzzing, they will refer to what is sometimes called like mutation fuzzing, where there is something that is kind of instrumenting the test and making sure that it tries to explore every code branch. With property-based testing, by default, it doesn't try and explore every single code branch. But instead, the thing it does is it uses structured data rather than the unstructured data that fuzzing has. So there's trade-offs in both directions. I found that those two things can often be used simultaneously, and one use that we used pretty extensively in my past life was where you use all of the work that you did for property-based testing. You use that to generate random corpuses for fuzzing, because all of these generate random values, and these random values are very high quality. And mutation fuzzing really depends on a high quality corpus to work really well. So you can generate pretty good random inputs from which a mutation fuzzer can get going. And I remember that being really effective because we were trying to fuzz a deserializer, and deserializers can often be really hard to make sure we're correct. So we generated valid values and then gave them to the fuzzer. That got bugs in like a few seconds, whereas if you just ran a fuzzer with no corpus at all, it would take like hours to find those edge cases.
That's really cool. I really like this example too, Rain, and it did get me thinking. I don't want to start a debate here, but it seems like we could use TLA plus for this too. For kind of modeling this kind of system with again all these kind of fiddly edge conditions, encoding the logic into TLA. I don't know. What do you think, Greg? Like, would this be a good formal methods example as well, or do you think it's not stepping on the toes of Proptest?
I think I think they're separate. I don't think it's stepping on the toes of Proptest. I think they're very complementary. One thing about schemes like TLA is that depending on the kind of data that you are working with, for example, you might find that TLA plus is just not amenable to the particular problems that you were working on for one reason or another. For example, if you're trying to do something with floats, no, sorry, you're going to have a bad time. There's not really a native, like floats have complicated semantics. That's not something that TLA plus does, especially well. I mean, I think a lot of the there are some cases where things can overlap. I think one of the things to keep in mind with the formal modeling stuff in particular is that the models aren't code and they're not the shippable artifact. And so, you do want to also make sure that you're bringing all of your powers to bear on making sure that the stuff that you've done that actually implements the design that you've got upholds all of the properties and invariants and things that you actually expect it to uphold, in that operating environment. So I think it can kind of be both and. Like there's probably, I'm sure that there are some cases where, like, if you were doing a brand new algorithm and you can specify it like in a model checked kind of way, you can certainly get TLA to do a lot of things in that respect. But there's still a lot of room too, I think, for good exhaustive test frameworks and sort of a broad spectrum of things, especially when it comes time to verify the things that you actually mean to hand over to your customers.
Adam's attempts to generate formalism Fight Club have failed.
Well, you got to try, right?
Exactly. But I think it's actually
I mean, so I mean the models are great. The point is that they only get you so far, right? And especially with very limited power for automated translation into things, you want to make sure, like, you didn't make a mistake then either. And that's where you want to have as many powerful testing techniques in your arsenal for your production code as you have for the designs up front.
Yeah, and I'm kind of like, I love the fact that these are kind of complementary, and because I mean, also, like, when you're using prop testing, it's like you're going to be bug for bug compatible with the thing that you are using as the oracle, right? So right now, it'd be interesting to know have you ever, in doing this, have you ever found that there's actually a bug in the thing that you're using as the canonical implementation?
So many times. That's like, honestly, like there are so many places in which there's like you've written an oracle, and so I think just like TLA plus, you're often in dialogue with the oracle and with the system under test, and you're like, oh, actually I didn't think about this edge case, and is this an issue in the system under test, or is it in the oracle? And that's where you have to think about it. I found that sometimes the oracle can even be more complicated than the system under test, and that's where it gets spicy. So as an example, so I wrote this Rust library called Guppy, and Guppy is a way to track and query cargo dependency graphs. And one of the things it can do is it can simulate cargo builds. And so you can throw it a given list of like packages in your workspace and what features are enabled and whether dev dependencies are enabled or not, and all of these other flags. And it will tell you which packages were built in the end. And that's a really, really cool set of things. That's a really cool thing it can do, but how do you make sure it's correct? Well, we have the oracle, and the oracle is cargo, right? So you generate a random query, you throw it at cargo, you throw it at Guppy, you make sure that they produce the same results. Now, it turned out that ended up finding way more bugs in cargo than it did in Guppy.
Totally.
So there's a whole list of bugs in cargo that it found. And so, who's the oracle now?
But that's really interesting. I mean, I think that it is actually kind of the power of having these different implementations that are operating under different constraints, or that you're taking in Guppy's case, it's actually trying to do something different than what cargo is doing, but it's trying to use cargo to validate that it's using. I mean, correct me if I'm misspeaking there, but it sounds like and so they, in other words, like, these are different things, but they have a very important intersection point where they can be used to check the other.
Exactly. They're completely different data structures with their own models and their own, places where they're meant to be used, and there are places where they do the same thing. And so you can compare those things to make sure that, if there's a bug in both of them, right?
So this is kind of asking you both like purely selfishly because it's a problem that's in front of me at the moment. But one of the challenges that we've got are in kind of dynamic systems where we are, and Adam, I'm thinking about some of our some of the age-old challenges about right transaction sizing with CFS, the size of the transaction group, and we see a lot of these things in a dynamic system where you kind of like, how do you've got throttling behavior and so on. Is there can formalisms offer us things where we've got these like very dynamic systems where the system is not it's not a question of correctness but one of optimality and of kind of eliminating queuing delays? And sorry to just be freewheeling here, I'm really asking you to do my homework for me because this is a problem that's right in front of us as we kind of tackle some of the performance issues in front of us. This is where I wonder, did Discord died again?
Yeah, that's right. You've disconnected. Don't worry.
I'm disconnected. Don't worry. Exactly. I know everyone's like, what is he even talking about? Like, what is this? God, how do I even tell him he's not even wrong? It's like,
Maybe a related part. Can we express constraints that are related to, activity or things of that notion? Is that kind of what you're getting at, Brian?
Yeah, I mean, just like how do we kind of model some of these more runtime aspects of it that are not necessarily invariants, but are. This is not a well-formed question. I'm realizing it. Maybe it would have been better off Discord had died. Discord did die. I mean, earlier the app actually croaked. I'm like, Greg is not getting my audio actually, but Adam, you can hear me. We've gone split brain.
Weird.
I can
We've
hear
had
you.
this before.
Are we being haunted by Twitter Spaces? Is it possible that
the ghost of Twitter Spaces? Yeah,
the ghost of Twitter Spaces. Musk is stabbing his Discord voodoo doll right now, right in the split brain, which is definitely we've had all sorts of is Greg? Are you trying to make some meta point about verification? Is this a verification joke? Is this verification humor? As Matt's pointing out, it is strange. Yeah, it is actually. Maybe we do need some audio problems just to kind of mix things up around here. It did got a little boring with the audio being so reliable.
That's right. No random crash of the Twitter app that brought everyone down. Yeah.
Oh my God! Especially going back and re-listening. I know you have Adam too. Going back and re-listening to some of our old spaces where it's like, okay, got another audio problem. All right, it's like, okay, guys, do you have anything else to talk about other than audio problems?
Yeah.
If there's 30 seconds of silence, Matt, that was definitely me saying what I thought was me making what I thought was an interesting observation, and then
but that was only the first 10 seconds. The next 20 seconds was everyone in stunned silence.
Stunned silence, right? Exactly. Well, look, I've been known to have conversations with nothing for plenty of times. So, where even are we? Where were we even talking about? Oh, you know what? Actually, we're gonna like never mention my question again. Let's just pretend I didn't ask it. And
there we go.
I'm gonna do better. Like, where are we? I think we're back on your moronic question. I think is where we were. It's like, you know what? Let's move off of that.
Well, we can come back in a couple of weeks when you've solved that bug and explain how formal methods had helped you.
Explain how far. What I think that I mean, what are some of the things to kind of look for? Because Rain, you were mentioning that you're kind of coming into this project at Facebook, and you've got this model, and you're kind of getting into prop testing as a way of checking the model. What are some things that people should be looking for and thinking about to like, boy, I need to go use prop testing, or I need to think about actually formalisms with respect to TLA plus and its derivatives. What are some of the what's some of the kind of the spidey sense you get when it's time to go to this particular tool?
Yeah, I do want to bookend this by saying that Proptest is a tool, right? It is not the be-all and end-all of testing. There are, other signs of testing, and everything have their own uses. But for me, I think when I have an algorithm which has fiddly bits where there are a lot of numbers and indexes where things can go wrong, then I'll be I'll be actively on the hunt for prop testing. I think another really common use case is anything that feels like it should round trip. I think that is another really, really good use of property-based testing, and that's where
Could you explain that?
serializers, deserializers. So as an
Got it.
example, so it's pretty common to have a serializer and a deserializer, and especially if they're handwritten. So this is a bit less of an issue with SERDI, but often if you're handwriting a deserializer or a serializer, you might want to make sure that everything round trips correctly. You want to make sure that you're not losing any data in the middle, and that the resulting value is the same. There's a really good list of properties on this in this blog post that I really like, because it kind of covers the general sets of things that you want to think about. And I think for me, the round tripping and also the actually we need to write a second implementation that has different constraints thing tend to be the most common places where I'll spot opportunities for property-based testing.
Okay, Rain,
that's
now Brian asked his selfish question. My selfish question is, I've got a collection of crates in this weird JSON schema universe where I take Rust types, generate JSON schema, and then reconstruct Rust types out of the JSON schema. A good case, do you think, for this kind of round tripping?
Oh, that seems. I think.
Or too
if
hairy
there's a
because we're
way-
generating Rust types in bizarre ways?
Yeah, there needs to be some notion of equality, I think, that you need to define between the existing Rust types and the new ones. So, I mean, one way you could do it potentially is by generating random values of those types and defining equality on them. Though I'd have to look at the details to be like if this is the right approach.
Okay.
But there needs to be some way of comparing equality there, and as long as you can define that, I think you can use this.
Gotcha. Cool. Thanks.
Yeah, that is really I love the idea of like looking for round tripping, of like when I send the system, I send the data through the system, and I basically should expect the same thing out if I go through, and that's a good candidate.
Yeah.
And then Greg, it sounds like from your perspective on using either TLA plus or again its derivatives, the PlusCal, what have you. It feels like when you're hitting the notebook and writing down it feels like it's a natural fit, obviously, for distributed systems. But what are the kinds of problems that are a particularly good fit for that kind of formalism?
So I think anything dealing with concurrency, the techniques in here are really, really powerful. This TLA in particular is a really great set of tools for being able to reason about concurrent systems with lots of things happening in lots of different orders, and the various interleavings that you have between them. Just to give a sort of spitballed number of that, I've got a model up here that I've been working on today that it has let's see, so it at its widest point had 86 distinct steps that it took, and 3,252,318 different distinct variable values that it went and iterated over. So lots and lots and lots of different state configurations of the system, and lots of different things that it can go and do. I do think that it's not limited necessarily to concurrency. One of the nice things about having to specify a model formally is that you have to be very precise and very well formal about the things that you are trying to express in the model. You have to make sure, for example, that all of your, if you're doing pure TLA, PlusCal will help take care of this for you, but in pure TLA, you have to be very explicit about all of your variables, even if they are not changing, have to be referred to properly in each predicate that you write and in each step that you take. And it becomes apparent to you, I think, as you write more of these things, what assumptions you are making and what things you are baking into the system that you are designing. Oh yeah, I have expressed this in such and such a way that I'm assuming that this particular thing is atomic, or that this happens as a transaction or something like that. And just the act of writing that out even if you just end up putting a comment there about, oh yeah, you know, we're assuming such and such, and so this condition has to hold in order for this to operate this way, it can be very valuable, I think, to have your thinking clarified by tools that are going to be strict with you about what things you say to them and what sort of notation you use, and how you've actually gone and expressed everything. So even if you are not necessarily dealing with a tremendously concurrent system, it can be, and you have a more straightforward algorithm that you're working on, it can be very helpful to go through the specification exercise just as a way of being forced to think about your problem very clearly and precisely before you sit down to write any code.
That's great. When I gotta say, this is something I love about Rust, and the kind of the rigor in Rust is that it really attracts people who are attracted to other rigorous approaches.
Yeah.
And I think that this is where, I mean, I don't think it's an accident that Rust is kind of a common thing that is binding a lot of this. And if you're someone who likes the rigor in Rust, you're going to like the rigor found in these other formalisms as well. And then, I mean, especially with Proptest, being able to actually kind of pull that in and really synthesize that, Rain, as you've done, it's really great. I mean, it allows us to not to generate more reliable, more robust software to verify that what we have written is what we intended to write, and it verifies what the way we're thinking about the system. It's just terrific stuff, honestly. And it's been, I also have to say, I love the fact that you are kind of coming from two different folkways, if you will, from Microsoft and Facebook, two different companies that were, I think people don't realize the degree to which the hyperscalers really are these larger companies, the FANGs, whatever you want to call them, whatever we call them these days, really are adopting a lot of these formalisms. And it's something that Microsoft has really been leading the charge on in a lot of ways. So it's really been fun for me personally to see the way you're using it at Oxide, and been super educational. And I need to find my own, just like it reminds me, Adam, of kind of like when I was looking longingly at Rust, trying to find the right problem to use Rust on. I feel like I'm looking for the right problems to use Proptest on, or to use TOA Plus on. So,
Yeah, totally.
Because I think you've not used either of these either.
No,
yet,
I haven't.
Right?
I'm already thinking about round tripping my way through my dumb, JSON schema stuff. But yeah, definitely looking for the next one.
Yeah, and I think that just to channel Greg's younger self, or being counseled by kind of a more senior engineer at Microsoft to really explore this stuff. I think it's going to be, when I get the opportunity, I'm going to be, or if and when you find the opportunity to use these formalisms, I want to really embrace it, because I think it's going to be it's really powerful stuff, and it's just fun to see again what the two of you have done. So thank you very much, Greg, Rain. Thank you both for joining us. This has been a lot of fun, and complete with some audio problems, so just like old times here. It's been great.
Thanks for having me.
Yeah,
thanks for having me as well. It's a lot of fun.
You bet. Keep Oxide and friends weird, as Matt was saying in the chat. Alrighty, well, we will see. I don't know if it's going to be next time or it'll be, but at some point, Adam, I think we're going to have to revisit async. I think
Yes.
Rain, we'd love to have you back for that as well. I think we're going to have to. We've had some async challenges as of late that I think it may turn into an async therapy session. So maybe we look to an Oxide and friends coming near you for some async love /therapy. All right. Thanks, everyone. See you next time.